Hello, everybody. Paul Taubman here with 9.Connects. Glad that you have joined us here today. You're in the right place if you are here for our webinar on test points. So let's get started with a few things here. Just some quick housekeeping, Q&A, possibly, I'd say very probably so today. So if you do have any questions, feel free to queue those up in the questions panel of the GoToWebinar panel there. And so we will be monitoring that throughout the presentation today. So you may get a response sooner than later. So do write those up, and I do think we'll have time. We added a couple of things here very recently, and I want to make sure that we had that time to go over those things. But based on my webinar runs, I think we'll have time to answer a couple of questions on the fly. All right, let's get on with it here. I'd like to start off with a polling question, and I'm really curious to know what the answer is to this. Are you using test points in your design? Wow, a huge percentage of you are using this. So I'm hoping that for today's presentation that you'll pick up a couple of gems along the way of things that you may be able to do. For those who aren't using them, hopefully by the time we're done with this here, you'll have a feel as to why you'd want to have these in there. But I'm really glad to see that that number is very high. And then I have another question for you. If you are doing or using test points, I'd like to know what the purposes of those are. So you can check more than one in this poll. All right, so let's take a look at this poll over here. So well over 50% of you are using them across the entire spectrum of tests for manufacturing, prototyping, and production over there. So this is really great. I'm glad to see that this is being used. I really didn't think that it was being used as much as what these numbers are suggesting. So let's take a look at this. And the reason I bring this up, and just to give you a little bit of a background about myself, I've been at this industry for quite a long time. I've been doing printed circuit boards really since 2007. But prior to that, really prior to my whole journey in the printed circuit board area, I did a lot of stuff in the test area. And it really frustrated me quite a bit because either I had to do the design for test because I was taking it cradle to grave, or because the companies that we were working with or I was working within, they had a design group and I was in the test group. So I've had quite a bit of experience in this area. And this is one of the things I want to talk about, because what I've seen more often than not is that design for test, which is a very valuable thing that you can add into the design, is something that just does not happen on its own. And more importantly, the bigger the company, the harder it is to get DFT incorporated into the entire flow. The bigger the company, the more silos, the more specialized you get. And that makes sense, right? A lot of times companies will organize themselves based on their skill set. So you have those people who are the circuit designers who are probably going to be in some type of design group, or you're going to have your libraries that are going to be handled by some type of component team, or you're going to even have your layout folks who are going to be just in one particular group because that's what they specialize in. So it happens quite often in very large companies. And unfortunately, when that happens, test kind of gets neglected because this area over here, which is designed, is separated off by this fabrication assembly. And there's a huge gap that happens, not only usually in terms of physical distance, like offices being completely different buildings, but also a time gap as well. So why is this important? Well, because a lot of times what happens down here in prototyping and production actually has to happen in specification. And these folks over here tend to be left out of that conversation because, and again, in larger companies, there's just a whole group who does specification. And who are these individuals? Well, a lot of times they're actually the systems engineers. And they're not just worried about printed circuit board designs, they're worried about the software, they're worried about multiple functions coming together, off-the-shelf units that are going to have to be placed with each other, the mechanical aspects of it as well. So this can get easily lost in a massive shuffle when you're putting together a really large project. So it does have to start in specification. It's got to be available in the library. So the folks who are doing the schematics in particular, they're not going to put something out there that they don't have a library part for. And more importantly, they're not going to ask for something if they don't need it or they don't understand the need for it. So I'll show you a really great example of this here in just a moment. Of course, it's got to be incorporated into the design. When we're talking about it being incorporated in the design, we're talking about the schematics, and it's got to be strategically placed in the layout as well. So if it's in the schematics, it's going to find its way to the layout. But what we don't really want the layout folks to have to do is to take guessing games as to, well, it wasn't in the schematics, but maybe the test folks might want that. And that's not really a good practice. Whatever we do in the layout should be adequately reflected in the schematics. And then here's a really, really great example of something we came across. We thought this was pretty cool when we were looking at various things in getting ready for this webinar. So this is actually a probe holder. And this is something that Tektronix, I guess, apparently makes available. And so I thought this was really cool. But if you really think about it, this is something for test. This is not really anything that's value add to the circuit itself. So if someone from test wants this, they're going to have the ability to talk to the powers that be who are putting this together to incorporate this into the design. This is not something that you're going to add in afterwards. It has to already be in the schematic. It's got to be a part of the bill of materials. It's got to be something that the layout is going to address. So that's a great example of something where, yes, circuit-wise, it doesn't add value, but test-wise, it adds great value. And that can only happen when everybody understands the need for DFT. All right. So when there are what happens when you don't have test points? So here's a couple of examples of things. Now here's an individual from Reddit, of all places, where they actually took a driver board and they decided to solder on to the vias so that they could actually get a logic analyzer on this. So that's what they did here. We'll talk about signal integrity towards the end here, and you'll be surprised that this probably worked just fine without any disruption to the actual driver. Also over here, this is something we wanted to show. So what we did was we basically took one of our boards here at 9.Connects, and my assistant Travis scraped off the solder mask here to show the exposure of copper. This is a very common practice with an X-Acto knife with a lot of people when they actually have to get to the trace or to somehow solder something onto the copper here. So this is not an uncommon practice that they will do in test. And here's another one over here, which is really interesting. They must have wanted to get a hold of this antenna here or inject into the antenna. And what I thought was really cool about this one is that this is a coaxial cable. So if you're familiar with coaxial cables, you've got two conductors in there. You usually have a webbed, you usually have something that's webbed for the shield or is normally associated to ground. And then you have a insulator in there. And then after that, you have another conductor. So you can see that is exactly what's going on over here. And they did a pretty decent job soldering this on, but you can see that they did a lot of rework to this over here. The point I want to make is that in all of these cases here, yes, the test engineer, whoever's doing the test, they'll make it work. Hell or high water, they'll do it. Trust me, I've been on the test floors and we've done some pretty miraculous things when it comes to tests, but they also take a lot of time. And so if this, for example, already had the BNC connector or some type or SMA connector or something like that, there would not have been all this extra effort having to be put into this. They would have plugged in and they would have continued on with it. So these are some really good examples of what happens when we don't have a place to stick a probe. All right. So what are the purposes of test points? Well, you probably saw that already here. There's really can boil down to kind of three areas. One is the purposes for manufacturing. We want to test things during fabrication, and we want to test things during assembly. So for those who maybe have not seen this or just want a quick refresher, we're talking about fabrication is the actual creation of the board. So when they're done with fabrication, the only thing that you're going to have left over when you're done is you're just going to have a board here. So they'll have the silks, and they're going to put down, they may put down some type of material over the copper to prevent it from corroding here, but they're not going to stuff it with any components. And what they'll probably do more than likely, if you ask them to do it, is that they're going to do some type of continuity check here to make sure that the copper was properly etched, because this is actually a subtractive process. And if you want to see more about that, we've talked about those in prior webinars. But then in assembly as well, this is the situation where you take all your components and you place those on here. And again, you'd want to be doing some type of testing to make sure that the board works, so that if it gets sent out to the field or sent out to put in a box and sold to a customer, that it's going to work when the customer plugs it in or uses it. There's also prototype testing here. So once this has been created, you usually create a couple of samples of these things, and then from there you want to test them out. And more often than not, there's going to be some issues. You go through what's called a debug process. You try to figure out why this thing is not working. And if it is working, that doesn't mean that's the end. It means that now you're probably going to have to characterize it. Well, yeah, it did work at this voltage. Can it work at this voltage, a higher voltage? Can it work at a lower voltage? Can it work in different temperature settings, for example? Like if you're doing military grade or avionic grade, they may be doing shake and bake or vibe or some other type of harsh environment testing on this to make sure that it's going to be able to withstand pressure or temperature or whatever else is being inflicted upon it, moisture, for example. And then lastly, there's also production testing too, and this is primarily for the purposes of really quality assurance. So one last test before you send it out, because obviously customers expected the work, companies don't want it back, right? And so every time you get a return over there, that's kind of unsettling. You don't want to have you don't want things to be returned because they broke from the get-go. So what are the types of test points that are out there? Well, we can really boil it down to two different flavors. There are the ones that you purchase, and then there are the embedded types. I'll talk about the embedded types in a moment. These are the kind of ones that you can purchase. This is certainly not a complete limitation of the ones that you can find out there in DigiKey. I think they've got about over 200 different flavors of these things. A lot of them are just basically different variations of what you see over here. So you have through hole and you have surface mount. You can see those examples here. So these two here are surface mount. These two are through hole. Let's talk about some of the advantages that we have. These are really, really useful for prototype testing and for debug as well. So you can do DC monitoring or sourcing. So you hook up a probe onto this thing. If you've seen the probes, they've got little hooks on them. Once you've got them hooked up, they're good to go. So if you need to inject some type of DC to power it, or you want to see what the voltage is on it, these are very useful for that. There's going to be no signal integrity issues on these. I can trust you that. There'll be less stress on the probes. So if you're not having to hold it there or stick it into a hole in the board, we'll talk about that more in a moment here as a way to keep the probe onto the board. But it's less stress on the probe to use these things. And they're really great for testing and long-term debug. And there are situations where you may have to leave a probe onto something for literally 2 or 3 weeks, if not longer, in order to fix something. Or in certain situations where it's like, look, I'm testing this board, and this board is supposed to interface with another product, but the problem is that that product is not ready to go. And so we have to provide those signals ahead of time so that we can continue to test this board before we interface it with this other board that is due to come. Of course, same thing works with signaling, monitoring, and sourcing, though be careful with this one because obviously if you're doing high-speed design, something like a through hole like this would not be as advantageous as possibly using something like this particular surface mount. So just be aware of that. Okay, what are the disadvantages? Okay, you got to add some more to the bill of materials. Reflections and signal integrity issues could arise with these, especially if you're doing very high-speed design. And again, I'll just reiterate the fact that we don't need to have to really worry about those for the lower speeds, but for the higher speed type of things with the larger bandwidth, we're going to have to deal with them. As I was mentioning, is that we will talk more about this towards the end, so we'll show you some examples of these things on the embedded side and what they may or may not do. And then lastly, there is the board real estate issue. So when you put these down, you're obviously going to take up a bit of real estate. So you may have a 10 mil pin, but then you've got, or pardon me, a 10 mil trace, but now you've got a 50+ mil test point that's sitting next to or on top of that trace over there. So it's going to take up some real estate. Plus, you also will more than likely have the silk screen as well. Okay. Now let's talk about the embedded types for a moment. So what we mean by the embedded types are just ones where you just leave the copper available for a test probe. So one thing you can do is a through hole pad at 50 mil hole. And so here's an example of this over here. And the reason why we pick a 50 mil hole is that that is big enough so that if you want to take a test probe, a lot of times they have a little end piece to it where you can take the end piece off and you just have the pin. You can stick the pin straight into the hole and it will be able to hold it. Now, please do make sure that you release some of the stress by taping up the wire end there or propping it in such a way that you're not putting all the stress on that pin, because you will break the pin off. But at least in this situation over here, if you got it, you can just stick it into the board and you can run with it. There's also surface mount openings that you can do here as well. So if you want to leave some opportunity to see something that's going to be possibly an issue, you can at least leave an opening in there. The only thing with surface mount openings, they're a little bit tough. If you do have to leave a probe on them for a while, it's going to get, your hand's going to get tired because there's really nothing to prop it up there. But it at least gives you an opportunity to see a signal, especially if that signal is coming in from, for example, a BGA where you can't get underneath it. So it's there, but it's kind of a last resort type of option. So what are the advantages? Certainly less in the bill of materials, less invasive to the signal. So that these, as opposed to adding these other creatures on that we just talked about. Well, I was going to go to the other slide, but I don't want to push it all the way back there. So, but if you look at the other ones, for example, they're definitely going to have more signal integrity issues. Here, we're going to be less invasive to the signal. There are some disadvantages to this here. There's going to be obviously wear and tear on the probe. So if you do stick it in the hole and you don't have that probe mount, there's a chance that you're going to damage that particular probe tip. So just be aware of that. And then there's the hassles of holding the probe. Is the joke always kind of goes, the good Lord gave us 2 hands, but in the test floor, about 4 or 5 hands would be more necessary. In fact, Christopher and I, Christopher is the owner of 9.Connects, were talking before this, and we were joking about our days on the test floors over there. And he says, it's kind of like playing Twister on the test floor because you never had enough hands for all the probes that you necessarily were trying to hold or to monitor. All right. Just to give you an idea of what this looks like, this should look pretty familiar to most people. This is not uncommon for most labs. When a board comes in, they're going to stick a bunch of probes onto this thing, again, for either debug purposes or for characterization purposes. So it will look like this whether you gave them test points or not. Okay? Why are they doing this? Because in prototype testing, they're going to inject signals. They'll have power supplies hanging on this thing. They'll have meters on this. They'll have signal generators on there. They'll have an oscope on there. If it's got an RF element to it, they'll have a spectrum analyzer on there. And there's many other things, a digital analyzer, for example. So this is a really good example of what you can expect to see in the labs. Now, on the back over here, what I wish they had shown is what they had in the back here, because there's probably a stack of boxes with all these things that they were doing here. But at least they show you what this looks like. Now, why is this important? Because if they get to this point and they're putting a lot of stuff on this to get some type of signal, and they realize that they can't get a signal, to take this, unstrip it down, get it over to a soldering station to do what they need to do, and then put this back together, you're basically talking about a day lost. So if you have the test points on there and they have to get to that point over there, you've got to save them literally hours, if not an entire day of effort to somehow find that pin and to get a probe onto it. So the other type of testing that they do is, or that we can do with test points, is manufacturing. So I call this in mass testing because you're trying to test a lot of things over here. And so this kind of boils down to something you may have heard of called like ICT, which is called in-circuit testing. And you can even boil this down to 2 different flavors. One of them is what I'll call flying probe, and the other one, which I'll talk about in a moment, is called bed of nails. Now, there are hybrids of both of these. So what I'm trying to do for the purposes of just kind of introducing you to these is just to talk about what they do in general. So the first type is what's called flying probe. The reason why flying probe is used very commonly, especially in fabrication, is that it takes a very short setup time for this over here, and it is testing things in a serial fashion. So if you can think of 2 probes that are literally flying about, and I'm going to show you a little GIF clip of this here in just a moment, but envision these 2 little probes moving very, very quickly across the board. That's what it's doing, but it's doing it pretty much in a serial fashion. And what is it looking for? These are really good for continuity tests. So what are continuity tests? Well, when they've made the board, the signal is going to travel from point A to point B. So they're going to check for opens. They're also going to check for power shorts against the signals as well. And they'll also check for resistances. So they may have had a point A to point B piece of wire, but the problem is that that particular copper may have been overly etched. And so it'll have a higher resistance because there's obviously a less of a width for it to travel through. And so that can be an indication that the board itself may not be, even though it does have conductivity, it may not have the strength, or it may have a reliability problem. So that's what they would primarily do with this. So let's take a look at this over here. Oh, and by the way, this can be used in assembly as well. And continuity is just as important in assembly, because if you think about it, it's one thing to test a board when it's bare. Now that if you put all these parts on it and you want to test it, then you'd want to be able to do this type of testing again. And the reason that's important is because, well, you just added in a bunch of components, and components may not sit right, or a part may have dropped off the pick and place system when it was placing it, or the orientation was wrong. So continuity will be just as much important on the assembly side as it was on the bare board side here. So let's take a look at this. This was a little gift I was able to pull off. There's a company called SPIA out there. Now we have, just as a disclaimer to them, they're not endorsing us, we're not endorsing them. I came across this because when it comes to flying probes, quite frankly, a picture may be worth 1,000 words, but this is almost priceless because now you actually see the flying probes in action, and this is literally what it is doing. So the setup time is not that difficult. You just got to give it its locations where it needs to hit, and once it's there, it runs these tests in parallel. You got to remember that continuity is a binary test, so there's going to be at least 2 pins involved in that testing here. And this thing looks like it's actually possibly running 2 or 3 tests simultaneously. Also notice this thing is doing tests on an assembled board, which is pretty cool as well. Okay, so that's this here. So if you want to see this, there's the full-length video on YouTube. And by the way, the music they've got to this is really epic. So if you have some time, take a look at that product that they've got out there because it's really neat what it can do. All right, let's take a look over here for bed of nails. So bed of nails is another feature. This is primarily going to be used for production. Why is that? Because there's a much longer setup time. Once you see this thing in action, you'll see why that it is. It's actually a custom fixture. This custom fixture is going to cost some money to make, probably in a couple of $1,000s, just because it's so custom. But the other thing that's important about this one too is that you really have to have the layout set up in such a way that is going to work for you. So the layout has to be already on some type of grid. You would have to talk to the assembler about what their requirements are for this. This is not one of those things you can say, well, we're already in prototyping, now let's go to bed of nails. You can't do it. This has to be thought of way before you even get to assembly. This has to be something thought of during the layout process. But once you got this thing set up, it is a remarkably fast test, and it can do more testing too. Now, the ICT, when they say ICT, they call it an in-circuit test, but when I went and looked a little bit further into this, what they're saying is that this is kind of what they call a structural test, which effectively, again, is a continuity test, which we just talked about here. So it is looking for what I'll call structural issues as opposed to functional or even programming here. But what this can do is it can actually program things on the board. So if you have a large motherboard, for example, this has a couple of chips on it that need to be programmed, you don't have to do that afterwards. This can actually do the programming and then it can run the functional test. So let's take a look at this one. So again, same company, different video, but again, I liked the product and it did a good job of showing what it is. So you can see that they actually do this one in 2 stages. So they've got the shuttle over here, and then when it comes down, they're testing the ICT side, so they're doing a structural test for continuity. And then over here, when they come to stage 2, you're going to get the programming, and they're doing the functional test. But look at how fast it is doing this. So for the amount of money you spend on this, if you're going to do thousands of boards or millions of boards for that matter, then you're going to definitely want to go to a bed of nails. So there's the other way of doing it. And this fixture over here is primarily the one down here at the bottom. This is the fixture that's going to cost quite a bit of money. Now, obviously, there's stuff they've got to do here on the top as well, but it's the fixture on the bottom that's going to cost a bit to produce. Okay, and just over here, I want to show you a few other little tips and tricks before we get on to the EDA side of things. Here is just, this is where we were first introduced to this. Somebody in this thing called the stackexchange.com under the electronics area came up with some really cool little things that they did. So they posted them and I thought it'd be worth kind of sharing with you. So this was the probe holder. So again, if you don't want to just rely blindly on your hole to hold the entire weight of the probe, you can do this to take the stress off of it. So it's kind of a neat feature. It's from Tektronix. Just going to forewarn you, they're a little pricey, but you know what? Compared to fixing probes, they're probably a better alternative. There is also another mechanism over here. This is just kind of being smart about it so you don't have things draped all over your board. And so keeping that stuff off to the side is really, really helpful. And then lastly, over here as well, you've got 2 pins. So you've got the pin over here, but you also have your ground. So you have to remember that these pins, in a sense, they are binary tests. So even though it's testing for some type of function on a single signal, you have to have a reference to something. And 99% of the time, that reference is going to be to a ground. So if you put the alligator clip on there like they normally have, then what you're going to have as a result of that is you're going to have a little alligator clip that comes off of this little latch or this little hook that they put on there, and that's going to create kind of a large ground loop. So if you want to keep that loop to a minimum, this is an idea that you can do. But again, you've got to think about how this is going to work on the board. So you're going to have some type of via or pad in close proximity of the test point in order for this to work. So those are the things we've got to take into consideration. All right, with that being said, let's jump over to Altium Designer. Now, I know we've got a couple of people here today who are not necessarily Altium users, but I think some of the things I'll show you will be applicable to what you can do in your tool as well. One of the things I wanted to show you is just the library. So I'm going to jump into the libraries that we've created here just to kind of give you a little flavor of what we have done. All right, let's go over here to the library and let's go over here to the item IDs. So one of the things we did here for the embedded, so you can see that we did ones for the keystone parts. Those are the ones that that actually have a little hook on them with a color code to them. So if you want to see what these look like, that's what they happen to look like here. And we just added some colors to these so that so you could make it a little bit easier as to understanding what colors they might be associated with if somebody was actually comparing the schematic to the actual board. But when it comes to the embedded stuff over here, what we did was we said, okay, for the surface mount stuff, we wanted to make it look very similar to what it would actually look like on the board. So if this was in this case, it is a square surface mount part, okay? And so we decided to make it red and make it look square. So it looks just like its footprint over here. Now, if you're using a different product and you don't use red for the top color and using another color, then there's nothing that stops you from making that color there. So again, that it matches up with the footprint that you're using. So it's just, again, makes it kind of viable for the individual to say, oh, you've got a test point here and this kind of looks like a surface mount pad. All right, this is what we'll use for that. The other thing I did, and I wanted to kind of show this, is avoid this type of thing. So, and the reason I wanted to show you this is because one of the problems is that if you go back to your schematic document from an elegance perspective, this works a little bit better because obviously it saves a little bit more space compared to having it hang off the line here. The problem with this over here is that there are 2 pins. And if you have 2 pins, that means you have to have 2 pads. And what you'll get ultimately is you're going to get a problem with the PCB dock. So in this situation over here, I am not going to be able to connect up this point to this point here because I only have 1 pin. I don't have, or 1 pad. I did not define a second pad in my library. Now, in Altium and probably every other EDA tool out there, there are ways of short-circuiting this thing to make this work. But if it's done right in the library to begin with, then I shouldn't have to go through that craziness of making rule exceptions or whatever other things that may have to be done in order for this to work within the design. So I did put that out there, but please be aware that this is not going to work. Because here you can see I don't have it. And yeah, there are exceptions we can make, but why go down that path when a single pin will do what is necessary? Let's take a look. Here's an example for a differential. This was a through hole. So again, we made this look like a through hole. And if the colors are different in the tool that you're using, make it look similar to the tools that you're using. Right? So that when I look at this, I know it's a through hole, for example. And for the differential, we did give a part A and we give a part B. And here's a single example of that as well. This is a bad example. So again, ignore the 2 pins. The single pin is what you'd want to use here. What about on the schematic dock? Well, this just kind of gives you an idea of what they are. So when they are on the schematic dock, especially in Altium Designer, the netlist is going to push all this information through rather nicely. So this is, again, you could, in theory, add these things on in the PCB layout, but now you're putting the onus on the layout designer to do this. This really ought to be incorporated into the schematic design, and it keeps the net list clean between the schematic and the PCB. So there you go. So these are the parts we added in. We go over here to our board, just to throw a little quick 3D at you so you can see what it looks like here. So you can see that these parts, again, these were from Keystone here. They're great, they're just really large, and we'll talk about signal integrity here in just a moment. So there is a real estate element of it, as opposed to something like these embedded ones that we added in. Let's jump over here. So we have these 2 embedded ones. This is the 50 mil hole, so it'll be big enough for a probe chip to be held in that hole. We also have this over here. This one's 18 by 8, the diameter is 18 on this one, which is big enough to hold a tip. It will actually hold it in place. That brings up another really interesting point here. I'm going to go into my test point library. One of the things I want you to notice, so I'm going to start off with this. This is a capacitor, and I'm actually on the top paste right now. But what I want you to notice here is that when we go into, for example, our SMT part here, we don't add the top paste in there. And the reason we don't want to do that is that if we do put the top paste on there and we send it through assembly, well, what's going to happen is this is going to be kind of a smooth, rounded surface, and the tip is going to slide all over the place. So what we want to do here in this case, let's bring up our properties here, is we actually, in a sense, want to remove the solder paste from this. Okay? And if we take a, oops, click on that again, cancel, let's click. Here we go. We'll drop this down over here. So what you'll see is that we actually changed the paste expansion rule here to -8 mils. My personal opinion about this is that, yes, you can rely on a rule in the PCB editor to do this. I personally believe that you should customize these and you should have manual control over this. This should not be a rule that's kind of driving everything, because it's really easy to overlook what one test point is doing versus another. The other thing that you'll want to do here, and this one's definitely somewhat, well, I should say definitely, it is important to consider this, that you should turn these on. If this really is a test point, then turn it on for both fabrication and assembly, because you can turn these things off later on. And that brings me to kind of an important point here about the board itself. So let's go to the 2D mode. So if we do have a board here, how do we get the test points out? And there's a couple ways of doing it, and I'm going to show you those ways, but you're going to be surprised that Altium is doing a lot more work for you than you realized. Okay, so there's a feature in the tool, and I'll start off with that. So we'll go down this path first, but then you'll kind of realize that there's other ways of doing this. In Altium Designer, there's this thing called Tools Test Point Manager. And I actually have a polling question for you. I'm kind of curious to know, has anybody used the Test Point Manager? So let's get that poll going. All right, so a good portion of you haven't, and a good portion of you actually have used the Test Point Manager. I'm hoping that you've had more success than I have with it. I'm going to show you how it works and what the limitations are, and feel free if you feel like I've overlooked or glossed something about the Test Point Manager. So the intention of the Test Point Manager really has to do with these little check boxes that you find on every single pad and via in your design. So if you go into the properties, you will always find test points at the bottom. And what the Test Point Manager is trying to do is turn on and off those things depending on the circumstance that you may have over here. So that's the intention of it here. Now, I'm going to give you my humble opinion about the Test Point Manager. To me, the Test Point Manager at times feels as though it is a fix for a library that should have had this to begin with. Very similar to in the schematic documents, they have something that's called a Footprint Manager. And to me, the Footprint Manager, there are times where you really do have to use the Footprint Manager. But to me, the Footprint Manager is very a last resort. And if you're using it constantly, that usually indicates that your libraries are not up to par. To me, in a very similar fashion, the use of the Test Point Manager a lot of times may indicate that your libraries are probably up to par, but they don't have a good definition of what's a test point. So that's kind of my take on this. But let's take a look at this feature here. If we go into our Test Point Manager, so the Test Point Manager is showing you all the nets that are here. They're going to give you a status as to what they are in terms of fabrication or assembly based on, does it find test points based on the fabrication. So if the test points were turned on for a certain thing, you'll say it's complete or it's incomplete. And then there's going to be a same thing for assembly. Now they call it in-circuit assembly. It's just assembly. Same thing here, bare board fabrication. It's just fabrication. There's not a whole lot of things you can do over here except for selecting things, clearing them, and assigning them. So if I go over here, for example, and actually before I do this, let me show you one other feature just to show I do have fabrication test points here. I'm going to go into the PCB filter and I'm going to type in is fab test point, and I'm going to press apply, and you're going to see that a number of these things have been turned on already. So those are ones that I've already enabled here. So if I go back in, I'm going to do a Shift C to clear that. I'm going to go back into the tools, the Test Point Manager, and what I'm going to do here is I'm going to clear all of them. And it will have cleared them all. So if I press close and I go back to my filter here and apply all, you'll see that all of these actually got turned off. So again, Shift C to clear this. If I pick one of these particular pads, and this through-hole pad, you'll notice these got turned off. So that Test Point Manager is going to go into the properties, all these things, and they're turning them off if I clear them, or they're going to turn them on if I tell it to assign them. So we go back over here and we can take a look at that. So under Tools, and again, our Test Point Manager, let's go back into Fabrication Test Points. I'm going to assign them all. So here they are going to be assigned. So now the question you may have to you is like, can you do any type of editing here? The answer is no. All you can do is clear it or assign them. And what's driving this thing? Well, the rules are actually driving this, and I'll show you the rules here in just a moment. So I'm going to close this out for a moment and just show you that when I click on this, I'm going to apply all. and here are my test points. I'm gonna forewarn you, I'm not getting some things I would expect to see. So for example, over here from J1 to C1, I would have expected both sides of C1 to have lit up. So there's a few things I'm not really getting as to why those are, and I'm hoping it's just me and not the tool itself. But nevertheless, let me show you where the rules are and how the rules are being applied. So let's go here into the design, and let's go into our rules. And you'll notice that there is a section here called test points. So there's 2 of them set up for fabrication, 2 of them set up for assembly. They look exactly the same for their styles. So if I click here for fabrication, let's bring that down here and we can see this here. So this is what it looks like for fabrication. And of course, if I go into assembly style, it's going to look the exact same as well. So let me just talk about the fabrication setup here. What this is trying to do is it's trying to find some constraints so as to whether you're large or you're smaller. So how big or small, and there is a preferred here, but it's really based on the min, the max, and also your hole size as well. So my understanding is that this over here is handling just the general size of it, and then if there's a hole associated with it, it will look in this here as well. You can also have clearances, so if you need to have test points spaced out, which like a bed of nails would have to have, you would probably want to make sure that these spacings are done accordingly, so that there's more space here. Now I've left them all at 0 just so that they would select them accordingly, but you'd want to have these certain spaces again if you're going to get a probe in there or you're going to get a bed of nails, a tester in there as well. You can allow sides in here, so you can have the top and the bottom turned on. Now I have found that the bottom is always given preference over the top. And if you want the top to have preference over the bottom, you'll probably have to create additional rules for this. You'll also notice that there's grid, or to use no grid or to use a grid, this would probably be turned on if you were going to make sure that you had stuff on the grid for the bed and nails testing. You may want to allow test points under a component depending on your circumstance. Like for fabrication, that's probably fine. For your assembly, you probably wouldn't want to have this turned on because in fabrication, you have no components at that point in time on there. They also have a rule scope helper here. So if you wanted to make this very specific to surface mount pads, you set the scope, and then over here, it will change the scope to something different. If you want to do it to all of them, you can turn this off and then you can hit the scope. The exact same thing works for the assembly side. But in addition to that, you'll also see that there's a usage. And the usage is whether or not something should be a test point. And you can do a single test point per net. This is really useful for functional testing. Or if you really want to have like one test point at each node, so you're like, look, I want to have these points at each and every single node there, then you can turn this on here as well. So that's what these rules are going to do. Now, can you run these like a DRC check? And the answer is yes. So that yes, let me kind of back up here. Under your tools, test point manager, if you want it to assign it and generate it, it's going to adhere to those rules, or at least I believe it's adhering to these rules. But if you want to use it just as strictly a DRC check, you can go into tools, design rule check here, and then go under test points. And then you'll notice that none of the on lines are turned on, which kind of makes sense. I don't know if you'd want to have that bouncing around while you're trying to put down something that's been classified as a test point, especially if it's a component. This thing might drive you a little bit batty at that point. But here, this is the batch. So the batch, the intention of this is to run this as kind of a last run through of all of your things. So you'd hit the design rule check and it would run it as a batch at that point. So it would tell you whether you had test points that are not adhering to the rules. So you can use it that way as well. The other way you can assign test points is you can certainly do a find similar object on those. So if I wanted to assign test points to all the top ones, for example, I could go into find similar objects. I can go to pad over here. Here's the fabrication test point. Let me see if I can move this so you can see it. Top, let's say I wanted all those that were different. So I could click on this here and I can press OK. So it should select all of those that are pads. It didn't pick the vias up, but it picked those things that are pads that have not been assigned. And I could just go back at this point and turn those on into the properties panel. So just as a quick refresh for those people who are familiar with 18 and beyond or haven't seen 18 and beyond, the inspector panel has disappeared. They've removed it because what you can do now is you can select multiple things and then make those changes into the properties panel. So if I click on this, this will now add those to all of those things that are selected. And as a quick sanity check here, if I do isFab test point for a filtering, all these will now get turned on. Okay, so it's another way of you handling this here. Now, can we get around the whole test manager thing? And the answer is yes. You can do that. Number one, again, if you have your library set up as to what things are test points and what things aren't test points, then some of that's going to be just driven by just having your rules in terms of the usage and more importantly, their placements. So you can use the rules to make sure that they're properly placed. But the libraries can tell you which ones are test points and which ones are not test points. But here's the thing, and I'm going to go into a file over here and I'm going to fabrication outputs. When you're going to create these things, you go into test point report. There's two sets of test point reports. Here's the one for fabrication. If you go to assembly, there'll also be a test point report as well. They look exactly the same. They act the same way in Altium. Why do I want to bring this up? Because there's some interesting stuff that happens here. So let's bring up the test point report. You'll notice that there are two formats. One of them is text, and CSV is effectively text, but they're putting commas in there. Really useful for when you're dragging things into Excel. But I'm going to turn on the text, and I'm going to turn on the IPC-D356A, and I'm going to run both of these. By the way, when you run these, it may squawk at me because I may have to run the Gerbers again if you can't find them. Yep, it did. But I will run, let me run the Gerbers really quick here because this is kind of an important thing I want to show you. And it's easier to see visually. So I'm going to go into fabrication outputs. I'm going to go into Gerbers here. I'm going to leave these the same. I'm going to say for plot layers, I'm going to just say used on, and I'll press OK. And then it'll generate these for me. Okay. The reason I want to do this is because now when I run the test list again, it will actually create a Gerber here and I can see where all my test points are. So let's take a look at that. So if we go into, pardon me, I've got to go back into my PCB doc to get to the right menu. Fabrication outputs, test point report. I'm going to run both of these. I'll press OK. So it's now going to take the Gerber here and it's now going to superimpose the IPC net list or the 356 on top of this. So if I bring up the Camtastic panel, and you'll notice that this is green over here, but let me just put this as a white so you can clearly see this. The IPC 356, as far as it is concerned, if it is a pad or something that is exposed, it now becomes a part of its list. So turning on or turning off the test point and the properties means nothing to the IPC 356A. So you can give this, you don't have to worry about any, if you want to just get fabrication testing done, you can work the way you're working, never worry about the test points, generate the IPC list, hand it to your fabricator or your assembler, and they can pretty much run with this because they can figure out which pads they want to use. Okay, it's all encompassing and you don't have to turn on anything. Now, what about exporting things that have specific information to them? That is done through the text. So if you remember, when I created this, I actually created two of them. Again, I got to go back to my PCB board here. Let's go to PCB fabrication outputs and let's go back to the test point report. So when I created this, there was a text file that was also created. Let's take a look at that text file. So before I do that, because it's going to show everything here, I want to give you kind of proof positive of what you're about to see here. I am going to go back into the tools and I am going to go into the test point manager. I'm going to clear all of them and now I'm going to reassign all and I'll press close. If I go back to the PCB filter, you're going to see that not all of them have been assigned. Okay. In particular, look at C1 and possibly TP9. Now let's go back and run this again because this will update it. So let's go into fabrication outputs, test point report. I'm not going to run the IPC 356 this time. I'm just going to run the text, pardon me. So let's run this. And it still kind of shows this, but again, this is the IPC one. What I really want to show you is what got generated. Let's go to text documents here and let's bring up the fabrication board here. So let's bring this one up and let's press open. And we should be able to open in the text editor that's in Altium. So as a side note, Altium doesn't give you access to their test report, their text editor like they used to. The text editor had primarily been an Altium Designer for their FPGA stuff. However, there is still a text editor in there. So if it needs to use a text editor, it'll bring it up. It's just that I don't know of a way to do and file a new text editor anymore at this point. The point I want to make is that if you notice in this list over here, there is no C1. Okay, so what this list did over here is it only picked those things that the test point within the properties for that pad had been turned on. So if you want a specific list, you got to run it as a text. If you want the whole list, then run it as a 356A, IPC 356A, and that'll get you the entire list. So those are the options that you have there with this. The last thing I want to talk about here, because I know my time is getting on, is I want to talk a bit about signal integrity. So let me jump back over to the board. Let's do a Shift-C to clear this. And let's look at these two here. So these are samples of embedded. So this one over here is pretty small. And if we change our grid, I'm gonna hit the G key, drop this to 1 mil, Control M, just to give you a kind of a quick look at this, as long as the hotspot doesn't pull me in over here too badly. There we go. Well, it's a little bit off. This I think is actually 16, but then of course, we just click on this here. We can get it this way too. It's actually 18. So this has an 18 opening. And then this one over here does indeed have a 50. Trust me on that. I was looking into it. One of the things that bothered me when I was doing the webinar was I said, well, am I going to tell them to put test points on here that are going to cause them signal integrity issues? So I involved Tom Cassidy, who has done webinars for us on the past in signal integrity. And I said, Tom, can we run some signal integrity tests on various types of pins? And so he was kind enough to do that for me here today. And I'm going to bring back my slide presentation so we can look at the results of this. So let's do this from the current slide. Okay, so what we did was we ran 5 cases. And the first case was just our baseline. We put just a line from point A to point B without any test point. Our second one was a surface mount, and he actually did it at the diameter of 50 mil. So this is much bigger than the one I just showed you. The case 3 was a through hole 50 mil, 70 mil annular ring. This is what we thought people would be able to use as a minimum. They wanted to actually have the scope probe stick into the board itself. Afterwards, after we got the results of this, what I asked for is 2 more test runs. And the reason why I did this one at 75 was because what I was concerned about was that if the baseline, which the width is actually 15 mils, so the width of the trace is 15 mils, what happens when this is actually 5x? So the width of this now becomes 5x. And so we did that for both the surface mount and we did that for the through hole as well, just to see what's going to happen with this. Now we can't take this blindly as gospel across everything. We had to set things up. So the baseline was a 2-layer stack up. So if this looks familiar to you, it came from that webinar back in the fall. And it was a 40 ohm impedance that we were looking at. So this is a DDR3 type of scenario where you have some type of processor or FPGA, and it is feeding into your memory, your DDR memory here. We had, as I just mentioned, a 15 mil trace. And the reason we did that is because it matched the pads here, so we weren't dealing with additional issues with having to calculate impedances that were off because of this here. So what are the things we had over here? Just got to remember that when we're dealing with signal integrity issues, we're not dealing with clock speed. We're dealing with rising edges. And this is what we have to base all of our calculations off of. So we have to know what's called the signal bandwidth. We again go over to the calculation that's created, that was recommended as a rule of thumb. This created, I have to be careful of the word created, but derived by Professor Eric Bogatin. He's the one who's written this book called the Signal and Power Integrity Simplified. And this is one of his recommendations, that the bandwidth would be 0.35 divided by your rise time. So in our situation over here, we're taking it from a DDR3 point of view, and the rise time was approximately 0.5 nanoseconds. So again, it's not about the clock, it's about the rise time of that edge. Our bandwidth would be up to 1.4 gigahertz. And just to keep it simple, especially when you look at these charts over here, we're going to keep it at 2.0 gigahertz here. So we want to look with up to 2.0 gigahertz on this. And just to let you know, these are what the other cases look like. So when Tom created these things, he had added in one case a 50 mil mounting pad. Another case, he had done the 50 mil hole, 70 mil ring. Then we went to case 4 and 5, where we basically took the same thing, but we upped up the sizes on those. So the pad is 75 here in case 4, 75 mil hole in case 5 with a 100 mil ring. So I do have a question for you. Before we do that, I'm going to bring this up here. I'm kind of curious. It is a polling question. So which ones you think will pass? Which ones you think would fail? So let's put that one up there. All right, getting some interesting answers over here. Well, I'm not going to give you what the answer is until we get to the conclusion over here. So let's take a look. What I want to show you first and foremost, this is the baseline. So again, what are we looking at? We are looking at the frequency domain. What we're looking here at the top here is what's called attenuation. Attenuation is basically signal loss. On the bottom over here, you're looking at reflections. So when you have an impedance change for whatever reason, you're going to get these reflections here. So this is the baseline. More importantly, the black line that we put over here, this is 2 gigahertz. So this is the area that we're most concerned with. Yes, it looks ugly here at 20 gigahertz. We can expect that at 20 gigahertz. But fortunately for our rise times, we're going to be right now here at the 2 gigahertz line. So let's take a look here. By the way, 2 other things. So this is just the time domain. This is what the signal looks like in the time domain. And this is the eye chart in the eye domain. And this eye chart looks really good. So when the eye is closed, that means that you have signal integrity issues going on here. With the eye being wide open like this, this looks really, really good. So the baseline looks great for 2 gig bandwidth. Now we've introduced the SMT 50, so the surface mount 50 mil wide test point. We also have the through hole. This again was 50 mil, 70 mil ring. Now it does look ugly down here. So yes, if you're working in the higher frequencies, this is really problematic. But again, we're working in the 2 gig area here. So the attenuation, quite frankly, is no worse than what we had if we had nothing on there. Okay. And if we look over here, it's like, yeah, you know, we're starting to get to a bit of reflection here. So there could be some reflection on this through hole. But the thing that we really got to look at now is the time domain. So here's the time domain for the surface mount 50 mil. Here's the time domain for the through hole. And they look great. So this is the signal here. And the eye curves look just as well. So the general conclusion we can make is that at 50 mil, whether it's surface mount or a through hole with 70 mil ring, we can get away with something like that, and it will not cause too great of signal integrity based on our conditions that we're working in. So this was good. And what I asked Tom about was I said, Tom, can we up it here? Because what I'm concerned about is that, again, I want 5x what we are starting with. So we had a 15 mil width line. Well, what if it's now 5x? So we did a surface mount at 75 mil. Okay, so you can see now the green. So we're doing the baseline. Here's the 50. And of course, the red line being the one that is the total baseline. But the 50 was the last one we just saw here. So let's introduce the 75 mil here. So obviously, there's a little more attenuation. There's certainly a little more reflection going on. But again, let's look at the time domain. The time domains look really good. So you can even get away with a 75 mil size SMT. What about a through hole at 75? Yeah, it's getting a little ugly. So, but again, you don't see much difference here between the original 50 mil and the 75 mil at the 2 gigahertz line here. Obviously, other things here, you have some major issues. So, but the time domain looks good. So both for the eye and for the time for the signal itself. So the conclusion that we can make over here to answer whoever answered this is that if you said none of the above in terms of which ones will fail, for our circumstance right now, none of the above will fail. So depending on the rise time, one can get away with some of the larger test points for both SMT and through hole, which is great because if I can put a big old hole in there and I can stick a probe in it, that's far better than me having to try to hold a tip onto a 15 to 18 mil opening in the solder. Okay. However, and this is the big part, we don't want you to walk away and say, oh, we can do this for anything. We really don't want you to do that. What we want you to remember is that this was dependent upon the rise time, ultimately your bandwidth that gets calculated from the rise time, the target impedance that you're trying to aim for here, and the stack up as well. So remember, we did a 2-layer board, but those through holes, you know, if you got a 20-layer board, those through holes are going to be a lot bigger. You're going to have other circumstances here, so you may not have something that's going to work as easily for you. If you want a review of this, please do take a look at the webinar that was done here. This is the Practical Aspects of Signal Integrity Part 1. Tom did a really great job of this. In fact, I reviewed it. That's why I actually went running to him. It's like, Tom, I remember your webinar. I'm concerned about signal integrity, and that's why we actually did these things here. So take a look at it. One other shameless plug I'll put out there for just a moment is that if you want us to calculate these for you, Tom's got this set up. So if you're saying, you know what, I don't need you to do a full simulation board 9.connects, but man, I wouldn't mind you telling me what kind of test points I can get away with, then we can do that for you, and that would be probably just as effective as us trying to do the entire simulation for you as well. So one last polling question I have for you. What'd you think? So, all right, thanks guys. So yeah, I figured that a lot of you, given that you've done quite a bit of stuff with the test points, probably have already seen quite a bit of this. Hopefully it was a good refresher. Hopefully I threw a couple of little gems at you that you can walk away with there. And there we go. So I am going to still try to keep this open for a few questions here, but let me just talk about 9.connects for just a moment. You are here for a reason, to learn about test points, purposes, EDA tools, and signal integrity aspects of it. But I also want to talk a bit about our training and services. For us, I know that a lot of people are now working at home. We've been doing this for quite a while. We are a virtual office, and we've been so since 2009. In the past, our trainings have actually been migrating over the past decade. In the past, we were always trying to do public trainings. We try to find some hotel or some place, a computer room that we could use where we could set up our stuff, and then we'd do a public training. We rarely do public trainings now. What we prefer to do is we prefer to do them on site. We own our own machines, and then we can be very personal about what you're trying to do. We can go off on tangents that are important to you and your company. Of course, with what's going on right now with this whole crazy world that we live in, we also do online coaching, and we also do trainings online as well. So if you are still looking for training, just because we can't come to the site or because we're not doing public trainings anymore, and we'll still do them if we can get enough interest, but we really don't promote them as hard and fast as the on-site ones. And by the way, they're just as cost effective to do on-site as it is to do public. But for the coaching and the trainings online, there's a couple of things we want to throw at you. Number one, it's not a recording. You're not buying a recording. We do this live, and it's for you. Okay? It's not e-learning where you're trying to get a bunch of different videos that you're going to pick and choose from. We don't do that. When you ask us to teach it, it's us being there. It is a live session. And of course, there's back-to-back feedback from, we want to hear from you. In fact, when we're teaching online, there's nothing more daunting when nobody has questions or nobody asks, interrupts and says, well, can you do this? Or wait a minute, I have a problem with this exercise. So it's as if we are really there when we're doing it. So that's what we want to bring to your attention. For more information, contact or take a look at 9.connects.com. We have all of our trainings up there. And feel free to contact us. We're very flexible in that regard. So yeah, it looks like we're all good at this point in time. So I want to thank you very much for joining us. If there are any other questions, feel free to write those in and we'll try to address those offline for you. So again, thank you for your time. Really appreciate it. And we will see you next month. We are planning to do our next webinar on the 29th of April. So with that, take care, be safe, be healthy. Have a great day.